Hello everyone, we are going to talk about logarithms in this video, and that's kind of a new concept. Although I showed you how to use the calculator and use logarithms to solve some equations, but today we're going to go deeper into exactly what a logarithm is and how do we work with them. So what are they? So we're going to illustrate with something we already know, solving some equations, right? So here my variable is the base, and so this is like a power function, right? Because I have an exponent as a base, a variable as a base, and then to an exponent. So how do we solve that? Well, we know that if we have x cubed, we're going to take a cube root of x cubed and the cube root of 27, right? So we're undoing an exponent with a root, and the index has to be the same as the exponent. So if this would be x squared, I would use a square root. If it would be x to the fourth, I would use a fourth root, etc. So the index would match my exponent, so that they're undoing each other. They're inverse operation of each other. And so that will become x is equal to 3. So what if I solve something like that? So here my variable is a radicand. It's inside a root. And that's a fourth root of x, and it's equal to 16. So how do I undo a fourth root? Well, you're going to undo a fourth root by taking it to the fourth power, because those two operations are inverse of each other. They're undoing each other, right? So, and remember when we did the rational exponent, how we said that can be rewritten as x to the 4 over 4? And what is 4 over 4? Is that not just the same thing as x to the first, which is just x, right? And this is why it would solve for just x. It would cancel the root. And so what is 16 to the fourth power? Well, I'm just going to leave it there as 16 to the fourth power, because that'll be a big number, right? So I'm just going to leave it there. So now, what if my base is a number, unlike here, but my exponent is a variable? That's what we call exponential functions, right? And what is the inverse operation of exponential function? And that would be logarithms. So for solving that, we would need a logarithm. I have an M with 3 bumps. There we go. So we need a log here. So let's talk about them. Exponential and logarithms are inverse of each other, just as multiplication and division. So even though those are long words, right, they're just inverse operations. They're undoing each other. So the first thing we need to practice is switching back and forth from one form to the other, right? Because when you're going to solve equation, if you're in exponential, you're going to have to rewrite in log, and if you're in log, you're going to have to rewrite in exponential to be able to solve your equations. So we have to practice that switching back and forth. So what is 2 cubed equals 8 in a logarithmic form? Well, if you recall when we did the things in our calculator, I always said the base of the exponent becomes the base of the log. So you have a 2 here as a base, the little number here, the subscript, which is a lower number, right, will be 2. And then whatever that exponential is equal to will be what's inside your log. So that will be 8. And then that will be equal to 3. So what you need to hear, or the way you need to read that in your mind, is 2 to what power gives me an 8? 2 to what power gives me? So the answer of the logarithm is really the power you would put to that base to get that number, okay? All right, so let's look at this one. 4 squared equals 16. So same thing, we're going to have a log base 4 of what the exponential is equal to, right? So 16, and that, again, the question is 4 to what power gives me 16? And we know that that will be 2, and that will then match what we have up here, right? Okay. 3 to the fourth equals 81 in a logarithmic form is log. The base of the exponent is also the base of the log. the answer to the exponential is inside your log, and then that's equal to the exponent. So 3 to what power gives me 81, and that will be 3 to the 4th. So the log, when you're evaluating a log, what you're really trying to find is an exponent. The exponent that you would have to raise this base to get that number. 9 to the 1/2 equals 3. So log base 9 of 3 is equal to what? So the first example might make you think that this value here is always smaller than this one, but it is not always the case, right? Because an exponent could be a root, as it is in this case, right? And so 9 to what power gives me a 3. I have to have something that makes 9 smaller. That has to be a root, right? It cannot be just a power, an exponent. So 9 to the 1/2 will give me 3, because a 1/2 exponent is like a square root, so square root of 9 is 3. Now we're going to practice backwards, the other way. So we have a log base 7 of 743 equals 3. So what that is saying is that 7 is my base, so it becomes the base of my exponent. So 7 to that power has to be equal to the inside of the log. And if you're not sure, check that. Do 7 cubed in your calculator and you'll see that you get 743. Log base 2 of 64. And listen how I read that, right? Log base 2 of 64 equals 6. So the question this is asking me is 2 to what power gives me 64, right? 2 to what power gives me 64? And that power right there will be 6. So we're going to keep going. Here we have a base that's bigger than the number, so just like we had here, so we know that's going to be a root, right? So the question we hear here is that base, the base of the log, right? So 125 to what power gives me 5? And that has to be 1/3, because 1/3 is a cube root, and the cube root of 125 is indeed 5. All right, so switching back and forth is important. So let's see if we can use some colors here and make it pretty. We get some different colors, and let's see what we can come up with. So I'm going to say A to the B is going to be equal to C. I was not sure what color would look different. That looks different, I hope. You can see that's a green and that's a blue, right? So now we're going to take this exponential form and we're going to rewrite it logarithmic form, right? So the base, so the log stays there, right? We're going to have a log there. But now what becomes the base of that log is the base of the exponent. So my green A there becomes my little base here, right? So log base A. And then what the exponential is equal to is what goes inside my log, right? So I'm going to have that inside my log, that's C there. And let's put that in purple here. And that's going to be equal to the exponent, so the B. And that's how we're switching back and forth, right? Exponential, logarithmic. So let's look at the graph and talk a little bit about characteristic, which is a good review of our very first unit anyway, right? Characteristic of exponential function versus logarithmic function. So this is your exponential, and I graphed it very generically. See how I didn't put a number there for the base. I just put a B there, right? To say any real number B, right? And then here, the log, I tried to write that with just like that, without having that 10 there, but the calculator didn't let me do that. It absolutely wanted for me to put that 10 in there, which was really weird, because normally a base 10, we don't have to write the 10. But it didn't want to let me do it, so there it is. So here is your exponential graph. Here is your logarithmic graph. So now let's talk about their characteristics and see what's going on here. So the domain of the exponential. Domain of exponential, remember when we talked about that in a previous video, we said the domain of an exponential will be all real numbers, so from negative infinity all the way to infinity, right? Those are nice smooth curves, and there is always increasing or always decreasing, which, do you remember what we call that? Monotonic. It's a monotonic graph. All right, what is the domain of the logarithm? Well, the logarithmic function never, ever, ever crosses the y-axis here. This is a parent function, by the way, for a log, right, of base 10. So if that's never going to cross here, then the logarithmic domain will be 0 to infinity, but not touching 0. And if it's not touching 0, you know we're going to have a vertical asymptote right there. What is the range? So the range of this one and the parent function we're talking, right? There is no vertical translation here. The range will be from 0 up to positive infinity, but it will never touch 0, right? Because we talked about how we have a horizontal asymptote there. And as x goes toward negative infinity, the y values are approaching 0, but they're never really going to be equal to 0. So this is the range for the exponential. How about the domain for the exponential? The range. Well, it comes from negative infinity, right? It comes up, 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 and then it slows down, but it's still going to keep increasing forever and ever. Even though it doesn't increase as fast as here anymore, it's still going to be increasing. So the range here will still be negative infinity to positive infinity. The intercept. So the exponential function, the parent function, does not have an x-intercept, right? We said it's not going to touch the x-axis. However, it definitely has a y-intercept here. And if you're not sure what that will be, it doesn't matter the value of b, right? Because this is where x equals 0. And when you plug in a 0 here, any number, whatever b is, to the 0 power will become 1, right? And we know that b is not going to be 0, because otherwise we don't have an exponential. Remember, that's a restriction. So this value, no matter what, the y-intercept is going to be at 0, 1, always. Now let's look at the logarithm. This one is going to be at 1, 0. I think you kind of see where I'm getting at, right? Now let's look at the asymptotes. The exponential graph has a horizontal asymptote, so that will be a y equal a number equation, right? And the horizontal asymptote is at 0, so the equation will be y equals 0. The logarithm has a vertical asymptote, so that equation will be x equals a number, and it will be 0, so x equals 0. And now, attention, attention. Remember I said those two, what are they for each other? They are inverse for each other, inverses. And remember, how do we find an inverse from an equation? We switch x and y, right? Switch x and y. So if this is my domain, those are my x's, they become the y for the logarithm. If this is my range, those are my y's, they become the x for the logarithms. So you see how those just have been switched, just like the inverses, right? That they are. And then look at the y-intercept. See how the y-intercept is 0, 1? Take that x and y and switch them. Don't you get that? You do, right? So see, all of it falls into place, right? And then the asymptote is at y equals 0, so the asymptote for the logarithm will be at y 0, but at x equals 0, right? Okay. So you see the connection between the two and how they're inverse of each other. And then I graphed here the graph of both of them together on the same Cartesian plane. And so here is my exponential, here is my logarithm, and then remember what we said, every inverses are symmetrical over the line y equals x. So I graphed in a dashed manner here the line y equals x, so you can really see how they're mirror of each other, right? There are two common logarithms, two bases that are very common for logarithm, and here I want to relate it to something. that you know. So let me get a sticky note so I don't scribble on our notes here. When we're writing, let's say I want the cube root of 8. Well, we know that this means this number, we're looking for a number multiplied by itself 3 times. That will give me an 8, right? So we know that's true. What if I say that? How do you know what I want? We're looking for a number multiplied by itself. How many times? That will give me 16. Well, we wouldn't hesitate. We would know it's 4, right? And we would know that they meant a 2 here, even though it's not written, right? Because it's the most common root. When we do a square root, we don't write the index because it's a common one. Well, the logarithms are kind of the same way. There are 2 common ones, and so we don't write their base because we write them so often that we just don't write their base, and we just know. So the first one is what we call the common logarithm. Common from the most common one, right? And it's a logarithm with a base 10. So if you see a log like that, that doesn't have a base written on it, then you know it's a base 10. And that's what I meant earlier when I said I really didn't want that 10 there, but the calculator just kept putting it in there. So a base 10 is implied if you don't see it. So when you see a log that's like that, log base something of 100 equals 2, that base you don't see will be a base 10. So that would be the same thing as saying log base 10 of 100 is equal to 2. And how do I know that? Because this number, that's the base of the exponent, becomes the base of my exponential, right? So the 10 I don't see to that power has to be equal to the inside of the log, and that actually does work, right? 10 to the second power is in fact 100. So again, when you don't see a base here, you know it's a 10. And I wrote it here to show you, but we really don't, right? Just like you would never put the index of 2 in a square root. So here again, we're wondering, what is that? Well, the base you don't see, when you have a log, log, right? Because be careful, in a minute I'll show you a different one. When it says log, log, then we know that's a base 10 to that power has to be equal to the inside of the log, and that also is true, right? 10 to the 4th power is 10,000. So that's called the common logarithm when it has a base 10. So what's the other one? The other one is used in so many ways, in science, in finance, in economics. It's really used a lot, and it's called the natural logarithm. And that's when you're going to see the ln. So you're going to say, well, Miss Williams, why are we writing ln if it's a natural logarithm? Why are we not writing nl? And this is because, and I put that down here with a little winky face there for those people who are in Latin. If you're in Latin and you talk about that, you will then kind of know that natural logarithm in Latin is called Logarithmus naturalis. Logarithmus naturalis, and so ln, and that's where the origin comes from, right? Okay. So the natural logarithm is when we have a base e. So the natural log has a base e. Oh, what is a base e? Do you remember when we just did compounded interest, the interest that were compounded continuously? We said e is going to be equal to 2.718281828 ... right? It's going to keep going forever and never repeated. I think after that it's actually a 4 and a 5, just so you really can see this is not repeating. So the base e, which is this famous number, this irrational number, is the base of the natural log. And so because we cannot use log already, because it's already used for the common logarithm, we're just going to write it like that. So when you see a logarithm that just says ln, you know you're talking about a natural logarithm with a base e. So what is that saying? Do you recognize that number? Look, 2.78128182, right? You recognize it? Oh, I have a typo. I'm going to fix it on your papers, guys. I'm going to fix it for you, but I have a typo. You see how I have a typo here? This should be 1828, not 8128. As I was reading that, I thought, something sounds weird here. Okay, I'll fix it on your paper. So what is that? The base I don't see is going to be a base e, because it's a natural log. So the base e to that power, so to the first power, is going to be equal to the inside of the log, so 2.71828128, blah, blah, blah. And that, in fact, is true. E to the first power is equal to e, right? And that's e, just e written differently. Same thing here. We have a natural log. We don't see a base, but we know that the base of a natural log is e. So what does that say? It says e to that power is equal to what's inside the log, which is the square root of e. Well, is that true? Well, it is, right? Because now we know, since we did the fractional exponent, that a square root can be rewritten as an exponent 1/2, right? So we know those two are true. So this is also a true statement. So two common logarithms. The common logarithm with a base 10 and the natural logarithm, natural logarithm with a base e. Oh, I would have to say a mouthful. Now let's look at some properties. A log base a of a is equal to 1. Well, why is that true? Because let's rewrite that in exponential and see what that says. This says the base of my log is the base of my exponent. The answer to a log is the exponent, and then that has to be equal to the inside of the log. Well, is that not true? It is, right? So we know that this is true. So that's one of our properties. Log base a of 1 equals 0. Well, let's switch it to exponential. The base a to that power has to be equal. We know that a and any number to the 0 power except 0 itself is going to be 1, right? So we know that's going to be true also. Okay, let's go to this one. So what is this asking us? It says a to what power gives me a to the r? A, so let's write it. A to what power gives me a to the r? This is what that says. Well, we know that's going to be an r, don't we? Has to be. So there it is, right? All right, so now let's look at this one. This one is showing the connection between the exponential and the logarithm very well, because they're both in there on that in that equation. We have an exponential as an a to a power. And the power itself is a log base a. So I need you to pay attention to the fact that I have an a to a power. A is the base of an exponent, right? And that's the exponent right there. And what is that exponent? It's a log with a base a. Those two bases are the same, so their inverse operation of each other, that's like saying 2 times 1/2. Well, that would be 1, right? Because 2 and 1/2, they just cancel each other when you multiply them. Same thing here. We don't multiply here, but the exponential to that same logarithm with the same base is going to just be m. And that is because I forgot how I wanted to write that, guys. That's going to be because switch to log the base here, so I'm going to have a log base a of m is going to be equal to the exponent here, right? So that would be log base a of m. You see how I ended up with the same thing by just rewriting that into logarithmic form. So here it's exponential, right? A to a power equals m. So the log of that same base of the answer to that exponential is equal to the exponent, which is itself that. So, and we know those two are equal because they're the same, right? Okay, product property. The product property really, you should see the connection between exponents, because what happens when I multiply two bases that have the same exponent? So let me get my little sticky note again here. So for example, if I would have 2 to the 4th times 2 to the 5th, what would I do? Would I not just say those are the same bases? So I'm going to say that's 2 to the 4 plus 5, therefore that's 2 to the 9th, right? When we multiply the bases, we're going to add their exponent. Now do remember that a logarithm is an exponent, right? So here I'm adding two exponents because those are exponents. So if I'm adding two exponents, what did I do to their bases? I multiplied them, right? So you should see the connection between the laws of exponents and the properties of logarithms. So that's just a property here. There is nothing to work out. So quotient property is the same thing, right? Because when we multiply something, when we divide, so if I would divide 2 to the 4th divided by 2 to the 3rd, for example, if I divide the same bases, I would just say I'm going to subtract their exponents, right? And so that's what we're doing here. Since logs are exponents, we're dividing two things, and therefore we just take their exponent and we subtract them. The power property says when you're taking a power to a power, what do we do? So if I had 2 cubed to the 5th power, so you have an exponent to an exponent, would you not just say that's 2 to the 3 times 5, right? We multiply them. So that's the same here. We're going to have a log base A of m to the r. And so that's going to be the same thing as taking, because you know how the whole logarithm is an exponent, right? The whole log is equal to the exponent. So if that's an exponent to an exponent, that's the same thing as multiplying the exponent. So I'm taking this r here and I bring it to the front as a coefficient, and now I'm multiplying them. So that's really what this is saying. Now this is a little trick that's going to help us to solve some equation, and it derived from this property right here. Because if you're taking, see how I have an r times natural log of a here, so if I take that r and I bring it back inside the log, then I would have an e to the natural log, and you know that e and natural log are inverse of each other, so they cancel each other. So I would just have that a to the r that I brought back in left over, right? So that's a little trick we want to remember when we're going to solve equations. Rewrite expressions, using the properties. So we're going to use the properties that we just talked about up here. 27 times x is a product, right? So I'm going to break those two up like we did m and n here by writing two logs that are going to be added. The base is not changing, right? The base is 3, so we're going to keep 3. So we're going to have a log base 3 of the first factor, 27, plus a log base 3 of the second factor, x. So that's just called expanding the logarithm. Same thing here. We have a division. It's a natural log, so we're going to keep that natural log. So the natural log of my numerator, x squared, minus the natural log of the denominator. You need parentheses here because you have more than one term inside the log, right? See how here I didn't really put my parentheses? It's always better to put them, but I really didn't because it was just a number. But now when I have an addition or a subtraction, I need to put the parentheses because otherwise we're going to imply only the x is inside the log and not the 1. So be careful that you don't forget that. But now we're not done here because we still have an exponent. And remember we said when we have an exponent inside the log, we can bring it to the outside as a coefficient. So we really want to expand as far as we can. So we're going to take that to the outside as a coefficient 2 times the natural log of x minus the natural log of x plus 1. And now it's as expanded as it gets. Log, we don't have a base. So do you remember what the base is? When you have that log log, what is the base? It will be 10, right? So this here is just saying 10 to the what power is equal to 10. Well, what is that going to be? 10 to what power is equal to 10? That would just be a 1, right? There is nothing to expand there. I'm done. Alright, so on this one I have a log base 5 and I have a square root which can be rewritten as a fractional exponent. Let's do that. Log base 5 of x minus 1, and a square root is the same thing as a 1/2 exponent. Right, now why did I want to do that? Because now I can take that exponent and I can move it outside in the front as a coefficient. So that's equal to 1/2 log base 5 of x minus 1. Now remember, you need those parentheses there. Alright, I have a base 10 as an exponential, and then I have a log base 10. You know how those two are undoing each other, right? That's what we talked about up here. And because they're undoing each other, that 3 is going to be brought back in as an exponent. So we don't do 2 times 3, we do 2 to the third. So all of that becomes 2 to the third power, which is 8. This one. So what we're doing here, we're practicing, right, to get ready to solve equation in the next video. So here I have a log with a base of a square root of 7, and I needed you to see things like that because they're not always just nice integer numbers, right? Life is not always nice and pretty and clean. Sometimes it's a little messy and we have to deal with it. So a log base square root of 7 of 1. Oh, but that's kind of cool, isn't it? Because what is the question this is asking you? The base of the log to what power gives you a 1? What is the number that makes anything go to 1 when you raise it to it? And that would be 0, right? So the square root of 7 to the 0 power is indeed equal to 1. Natural log of a cube root of x plus 5 over 2x. So I'm going to rewrite that cube root just like we did up here in exponential form. So natural log of, so we have x plus 5 over 2x, and all of that inside my log is to the 1/3 power. Now, the reason I wanted to do that is so I can bring that exponent to the front as a coefficient. And I have a natural log. Now, we still have a division, right? So I'm going to have the numerator, x plus 5, and then minus your denominator, and that would be 2x. And now we remember our goal here is to expand as much as we can. So now we can still distribute this 1/3, right? Because both of those were inside that root. So the answer finally will be 1/3 natural log of x plus 5 minus 1/3 natural log of 2x. And that's expanded. All right, we're getting there, we're getting there. One more page. One more thing to look at, change of base formula. This is going to be critical for you students who are using the TI-83, TI-84, because you're going to have to use the change of base formula to be able to enter some of those logs. Because your calculators, the 83s and the 84s, are really only taking the two common bases. So the common logarithm base 10 and the natural logarithm base e. For everybody else who uses the TI Inspire, you're good to go, but you still need to know how to do that because in your future math classes, you're going to have to use that for other things. So we still need to talk about it. All right, A is not 1 and B is not 1 and M is a positive real number. So those are just the conditions for me to be able to set that up properly. So the change of base says if you have a log with a base A, whatever that is, of M, you can change that to any base you want. So I'm just calling that new base base B, but it could be any base you want, right? So you can change that by saying I want a log base, your new base, of that divided by the log, your new base, of what used to be the base. See how that changed from being the base to now being the inside of the log, right? And your new base is just what you want. Now, they have to be the same, right? You cannot have one on the top and something different at the bottom. And so this here is just showing you that you can pick any base you want, but you could also just switch it to a natural logarithm, which in the future, like for those of you who want to take some calculus class or pre-calculus, sometimes we want to change to natural logarithm a lot rather than any other base. So that would just be the same. You have a log base A of m. So you're going to switch to a natural log, which is your base E, right, of what used to be inside the log divided by that natural log of what used to be your base. So just know the big number goes on top, and what used to be your base, the little number goes on the bottom, and you have the logs with your new base there. We're going to do some examples. So we want to evaluate log base 8 of 32. Well, I don't really know how to do that, right? But I can see how they both have something in common, like they both have a factor of 2 in common. So I could say, let's change that to a base 2. And so that will be a log base 2 of what used to be inside my log, right, divided by that log base 2 of what used to be my base. And see how now I don't even need to touch my calculator, because look what this is saying. It says 2 to what power gives you a 32. And we know that's a 5, right? Because 2 to the 5th power is 32. And this one says 2 to what power gives you an 8? And we know that's 3. So the answer would be 5/3. Now, if you put this in your calculator, or if you put this in your calculator, no matter what, you're going to get 5/3, right? All right, I'm going to go to this one, but I'm going to shift it over a little bit because I'm out of room there. So we have a log base 100 of 1000. So I'm looking, and you always look for what they could have in common. And I can see a base 10 in common here, right? Because 100 is 10 squared and 1000 is 10 cubed. So I'm going to switch to a base 10, meaning the common logarithm. So I'm going to say a log base 10, so I don't write it, right, of 1000 over a log base 10, so we don't write it, of 100. And then that's going to say 10 to what power gives me 1000? That will be 3. And 10 to what power gives me 100 will be 2, and that's your answer. Finally, we're going to do this one. So I'm looking here and I'm thinking, whoa, I'm not really quite sure what to do on those, right? Not quite sure. So I don't see a common factor there. Oh, but I should read, shouldn't I? It says we need to write that as a natural logarithm. So really, I don't have any option. I need to rewrite that so that my log, my base is E. So that will just become the natural log of what used to be inside my log divided by the natural log of what used to be my base. And that will be my answer then. Okay, when we're going to solve equation, we're going to end up with expressions that are expanded, and we're going to have to compress them, right, into one single logarithm, one single one. So the opposite of what we did down here is what we're going to do up here. So we have a subtraction between two logs, and there are coefficients in the front. So the first thing, I want to bring those coefficients back inside as exponents, right? So I have a natural log of 2 cubed minus a natural log of 4 squared. Now those are just numbers, so I could go ahead and do that, right? So that would be a natural log of 8 minus a natural log of 16. And now, because it's a subtraction and those two logs have the same base, right? They both have a base E. That's going to be subtraction means you're dividing the insides. The one that has the negative in front of it is always the one that's going to come in your denominator. And that comes from the fact that this is like a -1 exponent, so the -1 means move it to the denominator, right? Multiplicative inverse. So that would be 8 over 16, which of course we're going to simplify to 1/2. Now let's look at this one. We have the same thing, right? We have exponents in the coefficients in the front that are going to be brought back inside as exponent. Those are roots, square roots. So we're going to say, okay, a log base 5, and it's a minus between them. So this one will be my numerator, this one in my denominator. So I'm going to do it all at once, right? So be careful. It's a square root. So I'm going to have a square root of 3x in the top, in the numerator, over the square root of x, and all of that is in my root, in my log, right? So really, could I just rewrite that as a big square root of 3x over x? and then the x's would cancel, right? And so that would just be a log base 5 of the square root of 3. There we go. Try this one. We have a log, and it's a subtraction, so we know we're going to divide. The base is 10, and then this one has an exponent that needs to be brought inside here. I'm looking at that and I'm thinking, ooh, I don't know about you, but this sure looks like it can be factored. What would it be? It would be x plus 2 and x plus 1, wouldn't it? So I'm going to rewrite that like that. So I have a log, it's a base 10, right? And my numerator will be this, but I'm going to rewrite it in factored form because I'm hoping something would maybe cancel. And then minus, meaning that goes in the denominator. This 2 comes up here as an exponent, so I would have x plus 1 squared. And sure enough, that square is going to cancel with this, so the answer will be log of x plus 2 over 1 of the x plus 1 is left over behind, right? So that will be your answer. Okay, we're moving on, almost there. I have a log base square root of e for both of those, right? And then a plus between them, that means I'm going to multiply their insides. So that will be equal to, I'm going to write it down here, I'm going to have a log square root of e as a base, and then e squared, and because I'm adding the log, I want to multiply their inside, right? So I'm going to multiply that by e. So that will be a log square root of e cubed, right? And I'm going to leave it like that. Now, true or false. So two last things we need to check quickly. If it's false, we need to correct. So is this a true statement or not? So first of all, I don't know if it's true or not. So I'm going to say, let's put those question mark over those equal signs, right? Because we don't know if it's true. We're checking. Log base 7 of 2 plus a half log base 7 of x. Is this equal to that? So I'm not sure, so I'm going to check, right? I have a plus between the logs, meaning I'm going to multiply their insides, but this one has a coefficient that needs to be brought inside. So that will be a log base 7 of 2, and then I'm multiplying their insides, right? But that's an exponent of 1/2, so that's like a square root. So this is what this one gave me. Is that what I had? And it's not, right? You see how the 2 here is inside the root, but the 2 did not have a 1/2 coefficient in the front. So this one is false, and we just showed why. Let's look at the next one. So this one is in condensed form, and then they give us an expanded form. We need to check if it's the same. So we have a log base 2 of a. That's my first term, so we're good to go. Then that was in the numerator. That now we're going in the denominator, so we need a minus log base 2 of 3, which is what I have. And then there is something else in the denominator here, and it's still in the denominator, so I need another minus, and they have a plus, right? So if they wanted the plus here, we could leave the plus here, but then we would have to say both of those are in the denominator, and then eventually that negative will be distributed. So that's a false also. All right, go have fun with your assignment. Those are fun to work with, those logarithms.